Hi everyone, my name is Wally and today I'm going to talk about gravity. I will explain what it is, how it works, and will show how computer simulations help us to understand the universe. Everything, absolutely everything in the universe is based on four fundamental interactions: weak nuclear interaction, strong nuclear interaction, electromagnetic interaction, and gravitational interaction. In this video, we'll talk about the fourth one. Every object that has mass bends the space around it. This curvature affects the other objects, and for us it feels like attraction, just like in this video. By the way, this is a great way to visualize gravity. So every object, every particle, every single atom is subject to gravity. Everything attracts everything, just with different strengths. And to calculate them, we can use this formula. By this formula that Isaac Newton discovered in the 17th century, we can calculate the force of attraction that acts on two objects. Here m1 and m2 are masses of two objects. R is distance between them and G is the gravitational constant. In simple terms, the force gets stronger when the masses are larger and the distance is smaller. It's also important to understand that forces on each object are equal due to Newton's third law. Now we understand how gravity works physically. Let's move to the most interesting part, the 3D simulation of gravity interaction. I made the simulation in Unity engine because there it's simple to work with 3D. First, I should explain how the simulation will work. Simulation stores a list of bodies. Each body has mass, velocity vector, and position coordinates. Each step of the simulation, the program calculates gravitational force for each body in the list based on their masses and distance between them, using the previously mentioned formula. The only slight difference is that it doesn't use the gravitational constant, because it's very small, and we want the simulation to go fast to be interesting. Then we calculate acceleration. Here we use Newton's second law, calculating acceleration through dividing the gravitational force by the body's mass. After calculating acceleration, we add it to the velocity. Here we get velocity for the current step of simulation and can just move the body in the space on this velocity. And that's all. Yes, actually, it's very simple. I made masses of both bodies equal. Let's start the simulation. And you can see that it works. Two bodies move to each other and reach high speeds when approaching. I added velocity vectors to make simulation clearer. Let's add some velocity that is perpendicular to the direction to one of the bodies. They orbit each other, and you can see the whole system moving through space. Let's try to make the mass of one of the bodies larger. You can see that it moves less readily in comparison with the second body. Now, the mass of the first body is much larger than the others. It looks exactly like Sun-Earth or Earth-Moon systems. Here are some of the other configurations. The gravitational interaction of two bodies is very predictable. There are a lot of equations that can help to find the exact position of the body at the exact moment. But adding one more body to the system, the situation changes completely. The motion of three bodies with comparable masses is too chaotic. Things get much more complicated. In the gravitational interaction of three bodies, there are too many unknown variables. That's why there is no one universal mathematical solution. The only practical way to describe this motion is through computer simulations. Humanity found several special cases of stable three-body systems. But any minor change in the characteristics will lead to chaos. This is called the three-body problem. I visualized it in my simulation. Position of bodies are random and masses are equal. The system is highly unstable and eventually collapses. This is the simulation with random masses. And some other configurations. Let's add more bodies. Now it is an n-body simulation, where n is the number of objects. You can see that bodies collide frequently. In my simulation, bodies don't have colliders and can go through each other. Let's fix it. To make them solid, I just used unity sphere colliders. Now they can collide, stick together and form larger bodies from each other. By increasing the number of bodies, they start to look more like particles. Let's try simulating some interesting processes in our n-body model. If I ask which planet of the solar system has rings, you of course answer Saturn. Actually, other gas giants also have rings, but they are nowhere near Saturn's in size and beauty. The large question that was bothering humanity for years was how did they form? You might know the most famous and possible theory: destruction of Saturn's moon by Saturn's gravity. When a moon gets close enough to its parent planet at a sufficiently small distance, it collapses. The planet's gravity attracts the matter of the moon stronger than the moon's own gravity, which leads to its destruction. Then, particles spread across the orbit and form rings. I tried to simulate it. I want to show you one more interesting thing. What if we try to make a self-gravitating disk where particles move along the circle? The disk collapses and particles start to form clusters. It leads to the formation of large central bodies and smaller bodies in their orbits. It looks a lot like a miniature solar system, because actually star systems are formed in the same way. So, gravity may look like a simple force, but when many bodies interact, it creates incredibly complex and beautiful systems. With just a few equations and a computer, we can reproduce processes that shape planets, moons, rings, and even entire star systems. And this is exactly why simulations are such a powerful tool. They help us to understand the universe, even when mathematics alone is not enough.